Hello, my dear students, and welcome to the start for chapter number 3, titled by Atomic Radiation. In the previous two chapters, we have tackled together what we can put under the umbrella of optical communication. We first studied the guided medium used to transmit optical data, which is the optical fiber, either as a structure or as characteristics in the form of attenuation and dispersion. In chapter 2, we have a macroscopic view on the optical modulation and demodulation system, especially optical modulation, under the title Mech-Zinger modulators or MZM modulators. But if you remember in the first lecture or in the zero lecture in this module, we have mentioned that in order to make an optical communication system, you have to have an optical carrier, a coherent optical carrier, which is what we call laser or light amplification for stimulated emission of radiation. So, in the rest of the course, in the rest of the module, we are going to study together how laser is working, or the main concepts beyond the laser. We are going to investigate 3 successive chapters in this area, starting with atomic radiation, chapter number 3, optical cavity, chapter number 4, and the laser process in chapter number 5. These 3 chapters will somehow construct your understanding in how we can implement laser. We will consider gas laser as an historical type of laser. Maybe if we have time, we will turn over to the semiconductor laser, which is, of course, the most commercial one, and then we will terminate our module with how light is propagating, how laser is propagating under the chapter titled by Gaussian waves. So today may be considered as a turning point in the module. In the previous 2 chapters, we were more toward communications. Now we will go more toward electromagnetism concepts in order to study the phenomena of laser, of course, with the need of some prerequisite information from our semiconductors devices. So let's now start chapter number 3 under the title Atomic Radiation. Okay, so let's now start our atomic radiation lecture, chapter number 3. As I mentioned in my introduction, that this is a turning point. That's why we are going to start to use a new reference. Here we are going to use Verdine, and by the way, Verdine will be our main textbook during the coming 4 chapters, or actually the whole rest of the module. We will use Verdine as our reference. However, we are not going to use the same sequence like what proposed by Verdine. We will use somehow a different sequence. That's why our first or our 3rd chapter, by the way, is chapter number 7 in Verdine under the same title, atomic radiation. Additionally, you can use another external sources and lectures in order to get more engaged in this topic if you would like to. Okay, perfect. So let's now start with this. Okay, here, this is the discussion about the relation between temperature and light. So this is typical, some sort of flame where we have a variation in light to indicate different temperature. And my question in this slide, where is the highest temperature? In order to answer this question, we have to return back maybe 200 years ago, whenever people start to deal with a hypothetical body called the black body radiation. Black body radiation is a black body where it is characteristic by it has zero refraction, zero transmission, 100% absorption, and 100% radiation. As I mentioned, it's a somehow hypothetical body. So, whenever you have a black body and you start to measure the radiated energy from this black body, you will get something like that. Of course, as I mentioned, this is a hypothetical model. However, maybe during this chapter you will understand how we can realize such a model. Of course, not 100% realization, but to somehow to model experimentally the black body. But this is an experimental work implemented 200 years ago, maybe more, when they start to heat the body and measure the spectrum density and so on. As you can see, this peak which indicates the maximum transmitted or maximum radiated photon from the structure, start with the infrared region, which is above 800 nanometer wavelengths, and goes to the red, then we have the yellow, the green, and then it turns to blue and so on. So this can make the link between the temperature and the light. So the reddish light and the infrared, of course, indicates the lower temperature. And whenever you go to the green, yellow, yellow, green, blue, blah, 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 then you are going to higher temperature and so on. This is a relation. And based on this relation, people have extracted an empirical formula that can express the radiation density of what's called rho mu, which is equals to 8 by h, where h is Planck's constant, mu cube, where mu is the frequency, d mu, over c cube, where c is the speed of light, 1 over exponential h mu over kt minus 1. Of course, by replacing mu equals c over lambda, you can write the similar relation in terms of lambda instead of terms of mu, where you will find the relation which is inversely proportional to lambda to the power 5, instead of having a direct relation with frequency to the power 3. Okay, so this is simply an empirical formula which sustains without an analytical derivatives for tens, maybe hundreds of years. Maybe from your first impression, you will ask the question, what is the correlation between these slides and our optical theory? I hope that this answer comes through the slide during this lecture. Okay, now let's turn to another process. This process initiated by Einstein some years ago, but let's describe it in a very quick manner. We know that the main quanta of light is what's called photon. The photon is the quanta, or the smallest building unit of light. I believe that, I'm quite sure that all of you know this information. So, the question is, how we can generate photon? The simplest answer is that the photon is the transmission of energy process between two energy levels. So, whenever you have two energy levels and you have some particle, you have two main fundamental probabilities. Either to have a photon which has an energy equals to or greater than E2 minus E1, where E2 minus E1 is the difference between these two energies. So the electron in state E1 can absorb this energy in the form of a photon, of course, and then can use this energy to jump from the level E1 to the level E2. And this is what we call absorption. So you absorb the photon decays. Or the inverse process, to have an electron in energy level E2, and then this electron suddenly loses energy to drop from E2 to E1, and this lost energy, this energy difference, is reproduced in a form of a photon with an energy E2 minus E1. And of course, as you know, that the energy of the photon is equal to h times mu, where h is a Planck's constant and mu is the frequency. So depending on E2 minus E1, you can determine the frequency or the wavelength, of course, of this photon. So I think from your material semiconductor courses, it can be easily understood that these are the main two processes related to the photon, either to absorb a photon by an electron or a particle, or to generate a photon through the difference or the lost energy by pulling from E2 and going to E1. However, Einstein was to some extent different here, and he starts to mention another problem. Einstein, in the beginning of the 19th decade, starts to think about what are the probabilities whenever you have two energy levels, E2 and E1. Of course, there is an infinite number of probabilities, unlimited probabilities. However, from Einstein's perspective, he thought that there are three major probabilities which should be considered whenever we are dealing with two energy levels. These are the main important probabilities from Einstein's perspective. The first one was already tackled before Einstein, which is that emission process of a photon. We have an electron in E2. This electron will going to fall to E1, and then the energy conversion in this process, the energy will be converted in a form of a photon, which has an energy equals to E2 minus E1. But Einstein tagged this process under the title spontaneous emission, not emission overall or general, no, it's a spontaneous emission. And what we mean by a spontaneous emission is this output photon is what I can say, it's an uncontrolled photon. I mean, you have no information about the frequency of the photon, you have no information about the phase, the direction, the polarity. We don't have any information. Generally, it's a photon that is due to the falling of the electron from energy 2 to energy number 1, from energy level number 2 to energy level number 1. That's all. This is what we know about this. Herein, Einstein starts to think about what's called the rate equation. And generally, in order to understand the rate equation, I will go to some minutes to my whiteboard in order to describe the concept of the rate equation. Okay, so what about the rate equation? As I mentioned, we have two energy levels, E2 and E1. Both, of course, include some sort of particles, carriers, electrons. Now, what we are considering is the emission process, or what Einstein called the spontaneous emission process. So, we have some particles here. One of these particles will fall from E2 to go to E1. And a photon will be emitted with an energy E2 minus E1. Okay, so this is a process. If I say that the number of electrons in E2 is equal to M2, and the number of electrons in E1 is equal to M1. So we call this the popularity in E2 and the popularity in E1. Perfect. Then This popularity is for sure functional in time, because maybe some electrons jump from E2 to E1, or other electrons go from E1 to E2. Now we are focusing on one process only, where electrons are falling from E2 to E1. So this, let's ignore any other process and just assume that we have a single process, which is an emission, or what's called the spontaneous emission process, in the form of falling electrons from the level E2 to the level E1. That's why this N2 is a function in time, because with time, electrons will fall to E2 will decrease, or N2 will decrease. So what I'm going to write now is what's called dN2 by dt. What is dN2 by dt? dN2 by dt is the rate of a change of the popularity of the level E2 with respect to the time. And as I just mentioned, we are now considering only one process, which is the emission process. Accordingly, this number is a decreasing number because electrons are falling from E2 and down to E1. That's why we can start this equation with a negative sign, because the number is decreasing. Then, which number is decreasing? Is N2. Then we need the rate. How many electrons are falling per second, for example, from E2 to E1? We call this A21. So this is generally the equation representing the rate equation for the energy level E2 due to the spontaneous emission. We call this dN2 by dt equals negative A21, which is the rate, times N2. So for example, if I told you that 5% of the charge of 5% of the particle in N2 will leave N2 and go to N1 in 1 second, then the total reduction in 1 second, which is dN2 by dt, equals to negative the total number, which is, for example, 100 times 5%, then you will have negative 5. I mean, there is a reduction by 5 particles here. So it's the rate times the total in a very simple manner. Automatically, you can write an equation to express the rate of variation in the level E1 by saying that dN1 by dt equals to A21 and 2. Typically the same like the first equation, but without this negative sign. Because simply, whenever there is an electron leave energy 2, it will go directly to energy 1, because our model is a 2 energy level model. So this is the rate equation for the energy level E2, and this is the rate equation for the energy level E1. Both are the same, but in E2 we have a negative sign, and in E1 we have a positive sign. That's and this is the concept of rate equation. So let's now return back to our slides. Okay, so here is the process. Electron leave E2 and go to E1. Photon is emitted. It's uncontrolled photon. That's why we call it the spontaneous emission. And then we have the equation dN2 by dt. I am just telling that this is dN2 by dt only due to spontaneous emission is equals to negative A21 and 2. And this is the first probability considered by Einstein. As I mentioned, this probability was already previously mentioned, and just Einstein reformulated in this rate equation. Okay, what about the next? Again, it's already tackled probability, which is the absorption probability. You have a photon. This photon will be absorbed by an electron. So the electron will use the energy gained from this photon to jump from E1 and to go to E2. This is typically what happens. So in order to express this in a form of mathematical rate equation, you are going to say that E1, or again, let's start with E2. So dN2 by dt. Now dN2 by dt will increase. will increase with the number of electrons that will jump from E1 to E2. So it's the rate, which we call it now B21, and the positive sign because E2 will increase, and the stock is N1. You are taking electron from N1. That's why we use N1 here. But here we have something additionally appear in the equation, which is this rho mu. Why we insert this function, this a frequency dependent function? The answer is very easy, because generally, if you say that this photon will be absorbed and the electron will jump from E1 to E2, this is not correct, because there is a frequency dependent condition that should be satisfied in order to make this electron jump from E1 to E2. This frequency dependent condition is to have an energy greater than or equal E2 minus E1. If this photon energy is smaller than E2 minus E1, this photon will not be absorbed, or it may be absorbed, but it will not lead to a motion from E1 to E2. That's why this should be a frequency dependent equation, which is not the case for the first case. Herein, this is not a frequency dependent equation. You have a falling electron, an emitting photon, and that's all. There is nothing related to a condition or a restriction related to the frequency. Herein, you have a condition or a restriction related to the frequency, which is the energy of the incoming photon. As we mentioned, the energy equals h times mu, so the energy is a frequency dependent parameter. That's why we insert this rho mu to indicate that this is a frequency dependent process. So now, whenever dN2 by dt is positive, dN1 by dt will be a negative, because the popularity in E1 decrease, however, the popularity in N2 increase. That's why we have this negative sign here. This is the second probability. Okay, so let's now turn to the third process proposed by Einstein. Actually, the first two processes, or the first two probabilities, are already tackled before Einstein. This is a new one, which we call the stimulated emission. So please concentrate on it. Okay, so now the process is as follows. You have an incident photon, typically like the first case, which is the absorption case, or the second, sorry, which is the absorption case. So you have an incident photon. Of course, this incident photon has an energy, for example, E2 minus E1 or whatever, and has a certain direction, polarity, phase, everything. But for some reason or another, this photon will not be absorbed by the material. However, a falling electron from the energy level E2 to the energy level E1 will cause another photon to be produced. So you have now an incident photon, and you have now another photon which is produced due to the falling electron from E2 to E1. As an output, you have two photons and as an output, and one photon as an input. But there is a condition here that these two photons should be coherent photons. What do you mean by coherent is identical? I mean the same frequency, the same phase, the same direction, the same polarity. Everything is identical. If this condition occurs, then we call this as a stimulated emission. So this is the main difference, my dear students, between stimulated emission and spontaneous emission. In a spontaneous emission, you have what's called a random photon, uncontrolled. I call it an uncontrolled photon. It may have any type of frequency, phase, polarity, whatever it is, direction. However, in this case, you have what's called a coherent photons. You have a couple of coherent photons. Of course, you can consider this process, my dear students, as a amplification process. What's an amplification? We will come to this later on, but let me describe the main idea. The intensity of light is a direct function in the number of photons. So what happens here is you incident one photon, and after passing through the material, you get out 2 photons. So basically, you multiply the number of photons by 2, which means that you multiply the intensity. That's why we can consider this as some sort of amplification. Okay, perfect. Now, let's start to write a rate equation. Of course, the rate equation will be very simple. Again, we have a negative sign here because the number of electrons in the level E2 is decreasing. And we have a rate, but we call it now B21, not A21, just to distinguish between the spontaneous emission and the stimulated emission. And we have N2, which is the stock, the polarity of E2, where we are taking electron. But the main difference between the stimulated emission and the spontaneous emission is that this is again a frequency-dependent process. Because as I mentioned, your output photon should have identically the same frequency like the input photon. So we have this term rho mu. So you have to have the same frequency, same phase, same polarity, and same direction. And again, dN1 by dt is typically the same like dN2 by dt, but with different sign. I mean, we have a negative sign here because negative is positive. E2 is decreasing, so E1 is increasing. I mean, regarding popularity. So these are the 3 main processes identified by Einstein whenever you have 2 energy levels. Again, as Einstein mentioned, there are a huge, maybe unlimited number of processes. However, we are considering these 3 main processes are the dominating processes in our study for the 2-level case. Okay, as you can expect, generally, whenever you have 2 energy levels, these 3 processes can be implemented, can happen simultaneously. You can have an absorption and stimulated emission and the spontaneous emission. All are running. So what you can do is that you can write a general rate equation to describe the whole process of a laser. This is the general rate equation describing the whole process, saying that dN2 by dt, it's now radiated due to everything, is equals to minus A21 N2. This is the spontaneous one. You can easily recognize it because this is the only term which is not a function in frequency. Then we have B12 N1 rho mu. This is the absorption one. And then we have a negative B21 N2 rho mu, which is a stimulated emission. And as I mentioned, the relation between N1 and N2 is inversely. So whenever the N2 by dt is positive, we have to insert a negative sign here to make or to calculate the N1 by dt. Now this is a relation between dN1 by dt and dN2 by dt. What we are going to do, what we are going to implement in this relation. Let's see. Whenever you have a differential equation, I mean an equation changing with time, the easiest way to study this equation is to assume steady state, is to assume equilibrium. I mean, to assume that dN by dt is equals to 0. So that what we call the thermodynamic equilibrium. There is some sort of dynamic, but it's compensating each other. So that after the 3 processes, the number of the popularity and the level in the energy level E2, which is N2, is the same, and the popularity in the energy level E1, which is N1, is the same. So what we are going to do now using our white paper is to assume that this is a steady state process where dN by dt is equal to 0, and then we can determine a relation between n1 and n2. So let's do it. Okay, great. So what we can say that dn2 by dt is equals to, first we have spontaneous emission. Spontaneous means that we have an electron leaving E2 and going to E1, so it will be a negative. It's an frequency independent process, so it's A21 times N2, plus we have the second process is it's absorption. It's a positive because electrons are leaving E1 and going to E2. So we have B12, N1, and we have the rho mu. Then we have the third process, which is again negative, because electron again leaving E2 and going to E1 in the stimulated emission. We have B21 and 2 rho mu. Okay. Whenever you assume a steady state, that means that dn2 by dt will tends to 0 whenever it's a steady state. So if dn2 by dt will tends to 0, that's automatically mean that we can equalize this with 0. So simply I can turn this two terms to the other side with a positive sign. So we have n2 as a common factor, A21 plus rho mu times B21. This equals to N1 times rho times B12 rho of mu. Or generally, you can write an equation that N2 over N1 is equals to here you have this term, which is B12 rho mu over A21 plus rho mu B2. A very simple mathematical formula. So you have this relation. This relation expresses the popularity of N2 and the popularity of N1 as a ratio, N2 over N1. However, what is N2 and N1? Let's remember what is N2 and N1. So I will keep this slide with me as we are going to use this relation soon. If you remember, we say that we have two energy levels, E2 and E1. And the N1 and N2 is representing the popularity, the number of carriers here and there. If you have a good memory related to the semiconductor physics and the semiconductor devices, maybe you remember how we calculate the number of carriers by multiplying the probability to find the carriers times the number of states, if you remember. This process we used to do in our previous semiconductor devices. However, if you don't have this good memory, don't worry, we don't need this detail. But we can generally say that whenever we have two successive energy levels, for the first level N1, we have total popularity, which is equal to G1 e power or exponential n, where n is an any arbitrary number, n, h mu over kt. So, or accordingly, we can write an equation for N2, where N2 equals to G2, which again here represents the number of states, e power, and if this energy is nh mu, so by default, the next one will be n plus 1 h mu over kt. because the difference between these two levels is h mu. So h mu is E2 minus E1. So if this is n, then this will be n plus 1. So you have now an equation for n1 and n2. So you can write that n2 over n1 is equals to, the first one is g2 e power n plus 1 h mu over kt, and the second one is g1 e power n h mu over kt. Simply speaking, you can write this equation in a form of g2 over g1, and then we have e power h mu over kt, which is subtraction, because whenever you have a division with exponential, it's a subtraction of these two numbers. So this is generally the relation n2 over n1. g2 over g1, which is some number coefficient related to the density of states, or what's called the momentum number. We are not going to investigate this more. We are going to take this g2 and g1 as a constant all over our study, and this e power h mu over kt our out. So this is generally n2 over n1. But we have another relation to n2 over n1 in terms of our three coefficients a21, b12, a21, and b21. So what you can make now very easy is that you can equalize this with this. So let's turn back to our presentation slides. Okay, perfect. I believe that now you can see my presentation slide. So generally, this is the general. Okay, I'm sorry. This is the general rate. This is the general rate equation after considering the three processes: spontaneous emission, stimulated emission, and absorption. Then we are still under equilibrium, on the thermodynamic equilibrium. So we put this term is equal to 0, and we get n2 over n1, which is this equation. But from Boltzmann statistical point of view, we have n2 over n1 equals g2 over g1 e power minus, this minus is by mistake, I'm sorry, it's exponential e h mu over kt. So we have this term. Then you can equalize this with that, and you can, from this equation, determine the term rho of mu. Okay, so this will be the output: a21 over b21, 1 over b12 g2 over b21 g1 e power minus h mu over kt minus 1. But let's stop for a while and ask, what is this stupid mathematical steps? Why we are doing all these mathematical steps? Let's return back to the first slide in this lecture, which was the blackboard radiation. If you remember, I told you that this is an empirical formula which sustains sometimes tens or hundreds of years without an analytical derivation. Herein we have our analytical derivation. Herein we have this case. This what we have concluded from Einstein observation, and this is what we have empirically found whenever we look at blackboard radiation. And as you can see, these two equations are somehow similar. We have some coefficient, then we have 1 over exponential minus 1. However, don't forget that we have 3 hidden coefficients in Einstein. These are the 3 coefficients. So by analogy or by comparing this equation with this equation, you can find a relation between the 3 Einstein coefficients. Simply, this one is equals to this one, and this one should be equals to 1 here, which we are going to do here. So this A21 over B21 will be equals to this term, and this is equals to 1. So B12 G2 equal to B21 G. What is amazing here, what is amazing here, my dear students, is not only that Einstein have reached an analytical solution to determine the density due to a black body radiation, assuming the 3 main processes that can happen between 2 energy levels. But what is more amazing from my point of view is that we have a correlation between 3 processes which are, from our perspectives, totally independent. I mean, when we start explaining these 3 processes, we explain each one independent on the other, and we determine a rate equation independently, and then we just combine them mathematically, and that's all. But physically, they are totally independent. However, this is not true. What Einstein had proven that these 3 coefficients, these 3 processes are dependent. So whenever you can determine one of these 3 coefficients, you can easily using these 2 equations to get the other 2 ones, and they are dependent coefficients. I will consider this as the termination of part number 1 in our lecture dealing with atomic radiation. In the next part, we are going to illustrate together what's called the line width, which is one of the main important features related to the lasers. And this is the reason why there is no ideally or hypothetically coherent laser. So thank you very much for your concentration, and see you next part number 2 with lecture number 3, atomic radiation. Thank you, and bye.